Okay, so I'm sure at this point in our discussion of gas laws, you are thinking, well, these gas laws are fun and all, but I really miss stoichiometry problems and having a balanced equation involved in the problem. And if that's the case, I'm sure it is, you're in luck because that's what we want to look at now. So what we know about gases and what we've figured out we can calculate about gases is something that we can also extend to evaluating equations where gases are involved in the equation. Now, there's really two different versions we'll see with gas laws related to chemical equations. We're either going to do a stoichiometry calculation and then use that answer in a gas law calculation, or we're just going to reverse those steps. Maybe we have enough information to do a gas law calculation to get some information that's relevant to our equation, and then we're going to use that in a stoichiometry problem. It's really just a function of what information is provided in the problem. So let's look at an example of each and see how we might go about tackling them. Okay, so in this case, we've got magnesium. Can be used as, in quotes here, a getter in an evacuated enclosure to react with the last little traces of oxygen that are present in the atmosphere if you're trying to do something where you have oxygen sensitive chemicals and you don't want any oxygen. So we've got magnesium heated by passing a current through a wire of magnesium, right? And we're given the reaction down here with a balanced equation. Two magnesiums, solid phase, we're going to react with the oxygen gas and make two equivalents of magnesium oxide, which is also a solid. Now, what we're told is the volume of the enclosure, 0.382 liters. We're told the pressure of oxygen, so it's not the total pressure, there's an inert gas in there as well, probably nitrogen, but the pressure of oxygen in there is 3.5 times 10 to the minus 6th millimeters of mercury, and the temperature is 27. We want to figure out what mass of magnesium will react according to the following equation. Now, the important thing to recognize here, magnesium is not a gas. If we use the ideal gas law, we will not be calculating how much magnesium is going to be used. What we can calculate is information about the gas. So based on that partial pressure of oxygen, we can calculate how many moles of oxygen are in that enclosure. Then we can apply our balanced equation to figure out how much magnesium will have to react. So the first thing we want to do here is solve for moles of oxygen. So if we start with PV equals nRT, that means N is equal to PV over RT, and that we can solve for moles of oxygen. Okay, so the pressure here is millimeters of mercury. We want that to be atmospheres. We've done that enough that we ought to be able to do that maybe without writing it down. So let me take 3.5 times 10 to the minus 6th. Right? And then 1 atmosphere is 760 millimeters mercury, so divide that by 760, and that will be the pressure in atmospheres. So it's 4.605 times 10 to the minus 9th atmospheres of oxygen pressure in there. The volume is already in liters, 0.382 liters. Gas constant is 0.0821, and that's liter atmospheres per Kelvin mole. And the temperature should be in Kelvin. 27 plus 273 would be 300 Kelvin. And that will end up telling us how many moles. Now, keep in mind, we've got to be aware here in this type of problem, moles of what? Right? It's moles of the gas that's in that sample. So I've already got that pressure in my calculator, so times 0.382 divided by 0.0821 divided by 300. 7.1426 times 10 to the minus 11th moles of O2. Now I'm keeping a couple extra sig figs here, right? I can also keep that in my calculator. Once we get to moles, now here's a problem. If you're a little lazy with your units and you don't have O2 on there, you might say, oh, I got to moles, now I can just use the molar mass of magnesium and I've got my answer. Not so fast. Make sure you recognize you can only use the ideal gas law to calculate gases. So let's take 7.14 times 10 to the minus 11th moles of O2. Right? We look at our balanced equation. It takes 2 moles of magnesium for every 1 mole of O2 that reacts. That would get us to moles of magnesium. Then we can use the molar mass of magnesium. So 1 mole of magnesium. And I never remembered to look for my periodic table. Well, I have a textbook here. Let me just look in the cover of the textbook real quick. Magnesium is 24.31. 24.31 grams of magnesium per mole. So take that previous answer times 2 times 24.31. And it would take 3, let's see, we are actually limited to 2 sig figs by the partial pressure of oxygen. So this would be 3.5 times 10 to the minus 9th grams of magnesium. So it wouldn't take a lot of magnesium from that heated wire to react with all of the oxygen. Okay, but you do have to be careful about your units here. It's easy to kind of get caught with the wrong units. One more example here with stoichiometry. I said there were 2 versions of the problem, so here's the other possible problem, or type of problem anyway. The metabolic oxidation of glucose, which is C6H12O6, in our bodies produces CO2, which is expelled from our lungs as a gas. So there's the equation. We've got solution of the glucose reacting with oxygen, CO2, and water are the products. We want to calculate the volume of dry CO2, so we can ignore the water that is present as a product as well. Produced at body temperature, which is 37 Celsius, when 0.970 atmospheres of pressure, when 24.5 grams of glucose is consumed in the reaction. Now, what's different about this problem is the data we're given. We don't have enough information to use the ideal gas law yet. We have temperature and we have pressure. But the other component here is mass, and it's not even mass of the gas, it's mass of the glucose, which is in an aqueous solution. So we want to start this problem with our stoichiometry calculation. We want to start with 24.5 grams of glucose, and we want to figure out how much of the CO2 can we produce in moles, because moles of CO2 we can plug into our ideal gas law. Okay, so we need molar mass here, 1 mole of C6H12O6. Now these, I don't have to look up in the periodic table. I've got 6 carbons, so that's 6 times 12.01. I've got 12 hydrogens, that's 12 times 1.01, so that would be 12.12. And 6 oxygen is 6 times 16, or 96. So I'll enter in the carbon in my calculator and then add the other 2. 180.18 is the molar mass of glucose. So 180.18 grams of C6H12O6. Okay, so that gets me to moles. Now I can use the balanced equation. Every 1 mole of glucose will produce 6 moles of CO2. And that gives me moles of CO2, right? And that will be the missing piece I need to then do an ideal gas law calculation. So 24.5 divided by 180.18 times 6, 0.8159 moles. Keeping an extra sig fig there, we're actually limited to 3, right? Let's keep a little extra for that last calculation. Okay, now we've got moles, we've got temperature, we've got pressure. We're trying to solve for volume, right? How much CO2? So starting from PV equals nRT. If I want to solve for V, I divide through by pressure. So V would be nRT over P, right? I can plug in the moles that I just calculated. 0.8159 moles of CO2. Again, make sure it's moles of the gas that's in your equation. 0.0821 liter atmosphere per Kelvin mole is my gas constant, or R. 37 degrees C, convert that to Kelvin, would be 310. And divide by the pressure. The pressure is already in atmospheres, so 0.970 atmospheres. Right? Now, the only unit left here will be the liters. Moles, atmospheres, and kelvins will cancel out. This will give us the volume of CO2. So I've got the exact number for that previous calculation, times 0.0821 times 310 divided by 0.97. And to three significant figures, I would get 21.4 liters of CO2 gas here from this particular equation. So there's my answer. So, right, kind of combines two problems we've looked at in the past. Right, the gas law is a little bit new. So really kind of just like the other gas laws, it kind of comes down to evaluating your information. Do you have enough to do a gas law calculation? If so, that's what you'll do. And get some information that you can then relate to your balanced equation. If you don't have enough information to do a gas law calculation, then you're probably going to have to do your stoichiometry calculation first. Do that, get that quantity, how many moles of gas are produced or are reacted, and then you can plug that in and solve for whatever's missing in your ideal gas law. Okay, there's one more kind of general topic we want to talk about. We'll do that in the last video.